here's problem 2 from homework number 9, and so I have altered a very common Shigley problem. I changed the orientations of things and the parameters, but we want to design a shaft to withstand 2,500 kilowatts running at 1,800 RPM. And the shaft is made from AISI 4130 steel that's quenched and tempered at 540 degrees Celsius. In each gear, we'll have the shaft attached with an end mill seat. We need to look at that stress concentration up due to that. The dimensions are in the table below, and we wanted to design the shaft diameter for static loading based on yield strength and the maximum shear stress theory with a design factor of 1.5. And we can neglect transverse shear. Yay! Okay, so I have written this thing out and made sort of a little cartoon right there. Maybe I'll call this one FB, I think. So some of the first things, I don't have any geometry really to do. I could look up what my stress concentrations are going to be out of Shigley, and I said that was out of chapter 7. We haven't covered chapter 7, but we can certainly flip the book to it, right, and look for a table. Not too hard to do. And I think I did an example where I did this. So I showed what I was referring to were the keyways, and somewhere in here, I swear it's in here somewhere. There you go. First iteration estimates for stress concentrations for means of connecting things on the shaft. And we can see for the end mill key seat, in bending we have 2.14, and torsion we have 3.0, right? We don't really have much more guidance than that in Shigley, and not easily obtained. I do have some Peterson graphs that can maybe give us a little bit more, but it's honestly, it's just a really good first pass right here. So we will say for K, and we'll write from, should have done that in other ones, right? From table, I'll write tab. See, I saved 2 letters by writing this tab. KT is approximately, no, it is equal to, that's what it says from the thing, right? So we don't have to do approximately. 2.14, and KTS is 3. Okay, so what I want to do now is I want to find out what these loads are. So maybe I'll write that we're into the loads stage of the thing. And we're given 2,500 kilowatts and 1,800 RPM. And it's like, well, what do I do now? Well, we can find out what the torque is, right? So we go to the metric one of this equation right here, and we can find out what the torque is, knowing what the power in watts, not kilowatts, and the RPM are going to be. So we'll go ahead and do that and find that the torque is equal to 9.55 H over N. So 9.55, and we need 2 million watts. 1,800, right? 1,800 divided, and then 9.55 times, right? And I get 13,264 Newton meters. All right, well, let's let's make some FBDs and to see what that looks like. I'm going to take A by itself. So I'll have my FBD. I'll use the big circle here. I'm going to use up a lot of paper. Why not? And, I didn't bother to see where the center of that was. Let's see. So I'll make a shaft. It's going to be a pretty big shaft, I think. sort of like that right there. I don't know. And I didn't center it perfectly. Boy. All right, so that force that's going to be causing torque is coming down that direction right there. This is going to be and from our FBD, we are looking down the shaft. So here is the Z direction and the Y direction. So that's FAZ, and it's going to have a component coming down this way, which is our FAY. And then, so if that's going this way, that means that torque is coming this way. That's in the shaft. To be technically correct in an FBD, we should be putting our reactions in here, but can't quite find what they are going to be from here. But this is going to be, I'm just going to call it RY and RZ, just to keep it in there, right thing. So the sum of the moments about the x-axis are going to be a negative torque. I guess I'll go put the numbers in. I don't need to put in the symbols. I got the negative 13,264, and that's going to be plus FAZ, and the torque arm is going to be 1/2 the diameter of A. So we can just put it in, and I'm going to put it in as meters. So we can say that FAZ is going to be 0.25 divided by, it's going to be a large number, 53,000, is that right? Yeah, 53. I could turn it into KSI, so I don't have to write down a whole bunch of trailing zeros. I don't know, did that save any time at all? I don't know. I'll put it over here. We could find that, or do it underneath. FAY is just going to be this times the tangent of 20 degrees. So we get, it's going to be 19.31 kilonewtons. All right. Now, knowing that, we could go for the next one, because we wouldn't need to find out what this load right here is going to be. I think it's going to be easier to just do another FBD and then do it of the whole thing. We could do it where we cut the shaft on the other side, right? So we just did an FBD where we cut the shaft here and we looked over this one. We could cut the shaft there and then look over that one and do an identical thing because we have the torque bar. We could just use the thing. Either way, it doesn't really matter. And once again, I didn't really quite look and see where, I didn't line these up with anything in particular. So I'm probably going to be all screwy. I'll pick out that one. Kind of. And then I'll put, is that the one I used for the shaft? More like that one. And it doesn't matter. It's just for looks. There we go. So I put on that load and that. So here's your FAZ, FAY, and then on this one, this is going to be our FBY, and didn't really get that right spot, FBZ. All right. And my keyboard is in the way, so we will move him out of the way. Okay. All right. So let's see some of the moments. Well, I should put reactions up here. And I don't know what the direction they're going to go, but here's our R, Y, and our R, Z. Doesn't look like we read Z to. Some of the moments about the x-axis. I never put in up here. Didn't put it. Put positive. I'm not making very good arrows right there. All right, so we'll start out with this guy. He's going counterclockwise direction, and I'll use kilonewtons. It doesn't matter. See, I'm getting some kind of text right here. Oh, Larry's calling me. I don't know. I don't know what Larry wants. 53.06. And I could actually use millimeters. I don't need to use, meters necessarily in here. And so let me see. I'm distracted by Larry's phone call. 0.25. Yeah, that's the radius of the thing. I could use the diameter too, so they're just going to cancel out. So now we're going to go minus, I meant to put the force there first, FBY. And then times the radius of this, and that's 350, so that's what, 175? Or 0.175, because that's why for some reason I'm using the millimeters in here. And I'm going to get FBY, and he's going to be 53.06 and 0.25 times, but 0.175 divided, and I should get 75.80. Let's see what I got over here. I actually get 75.79. My numbers are going to start drafting off because I don't use kilonewtons. I'm going to start newton meters. Got to pay attention to this stuff, right? It's Larry's fault. We're going to blame Larry, okay? FBZ is going to be 75.80 times the tangent of the pressure angle of the gear, 20 tan times, so it's 27.59 kilonewtons. Yeah, okay. So now we have these forces. We need to do the shear moment diagram, which always takes a little bit of time, right? Nobody likes doing it. Nobody really enjoys doing the 3D shaft problems, but what have you. It's a good problem, I think. Let's see, where's my little ruler go? Where'd the little ruler go? He disappeared. Probably want to move the keyboard. You might have moved over. No. Oh, there he is down there. Okay. So this is problem 2 continued. ... And we'll do it all across there at once. Lazy. Oh, that was a terrible line. This makes for great video. Should play some kind of interesting background music while we're doing this, right? I should write my own music and play it during, so like the YouTube audience I could be discovered. It could be a big hit, right? Sure. Nobody wants to hear your crappy music, man. That's what I learned early on as a musician. Nobody really wants to hear your originals. They just want to hear something that they already know the words to. That's what they want to hear. Did I make that symmetric? I think so. 1, 2, 3, 1, 2, 3. No, I guess not. Right. My parallax error betrayed me. And this one's just slightly smaller. It's just a cartoon, really. Didn't do that one either. I didn't even draw the line. Okay, let's see. Erase that so it looks like a gear, kind of, and end it like over here somewhere. There you go. Do the same thing over there. So we're gonna erase these. I know. What's so exciting in this? It looks like 4 over there, and so like over here, and it goes to there. Something like that. All the way down. Yeah. There you go. And then thusly put them in there. Is it only 2 up, 2 up, 2 down? Huh. I really messed that one up. Oh well, okay. And then end it over here somewhere. There we go. So this is going to be our, I should be pausing the video while I do some of these things, make the video shorter. What do you think? I don't know. You're talking to yourself again. Yeah, that's what I do. I make these videos. I'm talking to myself all the time. All right, and while we're here, I'm going to go ahead and make my shear moment diagram thingy. So if you want to jump to the end of this, right? You can always fast forward all this stuff, right? Let's see. So let's look at our forces. In the y direction, we're going to have this guy right up there, and that's going to be, I'll label him in a second. This is going to be upwards, right? It's going to be upwards here in this view. And then in this view, we're going to see this force right there. Going to be that z direction of that. And then in this one, we are just going to see this view right there. Right. And in terms of values, let's see. We're going to have this guy right here is going to be the 19.31 kilonewtons. And this guy is going to be our 75.80 kilonewtons. Let's hope that doesn't get interfere. Maybe I'll make him a little shorter. A little shorter. Maybe. I don't know. Let's see. This guy is going to be our z direction up here. So that's going to be our 53.06 kilonewtons. And this one here is going to be our 27.59. I'm pretty sure BZ. 27.59 kilonewtons. And our dimensions, let's go back to the beginning. We had A, B, C. So we had 250, 450. So I got 250 here, 450 here, and 300. So 250, 450, and 300. I have a department meeting soon, so I gotta get move this thing along. All right, so our reactions. This is one of those teeter-totter things where it's kind of hard. You're gonna have to be careful. You're almost certain for this large value that you're gonna have a reaction right here, and that's gonna be our RCY. This one, it depends on what this value is and these distances. I'm gonna guess upwards. I just had to be prepared to be wrong. And that's going to be Roy, not Ray. And this one for sure, confusingly, because that axis thing makes it look like it's part of that. Let's see. Continue this, make it just a little lighter. Go Z right there. So here's going to be our ROS. Definitely going to be up because of this very large value here. And then this one, yeah, I think this one is going this way. So these are my predictions, and that was ROS. This would be RZI right there, RCZ. So we'll take the sum of the moments about O here, and we start out with a negative number, right? Because we're going clockwise. So we have 1931. I'm going to use millimeters because it's just easier. That's going to cancel out anyway. And then this one is going clockwise, so we got the 7580, that's the large number. And then we need to have 250 plus 450, so that's 700, yes. And now lastly, this is the thing we want to get, and he's negative here, RCY. And so that should be 1,000, right? Or 1 meter. So we should get RCY at 19.31 times 250, 7580 times 700, subtract it, divide by 1,000. And I'm going to look at my signs real quick. I think I got it right. 48.23. Let me just double check here. Because I subtracted that from here, which gives me a negative number. I don't know. Let me double check. 75.8700. Right. That's a positive, and now I'm going to subtract out 19.31. Yeah, 250 times. Subtract it. That is a positive number, and then that's going to be a negative side. So that is correct. Okay. Just trying to gotta make sure. That's the reason why we methodically do the thing, so we get the positive and negative things correctly. That's one example. So we have the sum of the forces in the y direction equals 0. I didn't pause there with that part. Here we go. And so we're going to say Roy, and then minus 19.31, and then plus 75.80, and then we're going to go minus 48.23, and Roy is going to be equal. Okay, now here we got to be careful again with these because we don't know for sure of the sign of that, right? So I'm going to start with this guy, and I'm going to subtract out him, minus, right? Now, oh, I think I got something wrong there when it came to values. I'm a little concerned. I think I'm okay. I want 75.8 and subtract out 48.23 and now subtract out 19.31. And I still have a positive value. So Roy is actually in the opposite direction. I would actually get a negative 8.26 kilonewtons. Got to be careful with these, right? So that means that it's actually coming downwards. Yeah. No. I shouldn't write it that way. My bad. Bad man. 8.260 kilonewtons downwards. There you go. Don't want to put the gonna remember that when I come back over here. And so I don't erase personally. I go ahead and circle the thing and then write in the arrow, right? Just to remind myself that I initially had the wrong thing. And then I take the sum of the moments over here. I'm going to do the same thing. And we can check this, by the way, by way of our, when we do the whole shear moment diagram, we could double, triple check that we got that correct. What a pain when you find out that you didn't get it correct, and then you have to go back and troubleshoot it. But anyway, so let's see. We're going to go clockwise with our 53.06 times our 250, and then plus our 27.59 times our 700. And then once again, we're going to have a negative RCZ times 1,000. And I didn't stay within my margins. So my RCZ, worth doing slowly here once again. I'll start with this one, make that positive. So 27.59 times our 700 is positive. Now let's take our 53.06 to 50 and subtract it. All right, so that's a positive number now. So that's negative. So that, okay, so we're going to be fine when we divide by our 1,000. And we get a very small number, 6.048 kilonewtons. All right, that's okay. This was a teeter-totter, and this was the most uncertain one right there, right? Because this is the one that's next to the large number. This is almost certainly going to be this. This one really kind of depends on the teeter-totter nature of the proportions of the thing, and can give you the unexpected result. That's why we do free body diagrams, and we're very careful with them. It's because we want to get the correct results. All right, so in the z direction, I'm actually predicting negative because downwards is positive. And then plus my 53.06, and then my minus my 27.59, and then this is a positive 6.048. Equals 0, so we get the ROI, and 53.06. My calculator buttons are sticking, which is probably the source of any mistakes I've been making lately. Maybe it's time for a new calculator. Stop spilling stuff on your calculator. That's what you do. Okay, I'm going to subtract that out. Great, I'm still a positive number, so I'm going to add this 6.048 added to there. That's negative, so this must be the answer of 31.52. I got my meeting in 10 minutes, and I haven't eaten lunch, so I might pause this. Pause it. There's a long pause. You can see the timestamp at the bottom. I got 12:35 right there. I bet time is going to fly, and then I'm going to have some students come by for office hours. So yeah, this video might extend several hours long. Okay, well, whatever, man, because I need to eat. But let me double check my values here, because I have them written down. I have my 35.12, right? And where's my other reaction right here? I got 8.25. Okay, all right. I think I got it correctly. I'm on the right track. Really long problems, I know. We'll pause. I think I'm back. I think it's going to keep on recording, right? It's like 4:11, so there's a big old time warp. Let's see here. Okay, so I need to do my shear moment diagram. So I had 8.26, and that's going to be pretty small, actually, I think. And let's label this V and M, and this is going to be in kilonewtons. Squeeze it in there. It's going to be Newton meters when I get down there. And so there's going to 19.31. We're going to add that. Okay, so maybe I put this in there. It's going to be the negative 8.260. And then we're going to combine that with 8.26 and 19.31. Add them together. So we get a 27. Something like that. So it's a negative 27.57. And then this is going to be not proportional. This isn't going to be to scale. But we're going to have 75.80. 75.80. And so we're going to get 48.23. Which we better get, because that's the other reaction, right? It needs to be brought back up to 0. And so we go to do the moment side of the thing. All right, so this is very small, so it's going to have a pretty small slope right there. And then this is going to have a larger slope. We get to right there. And then this one better return back to 0. And it might be good to check that it does return to 0 right in there. So let's take the negative 8.26 and multiply it by 250. 8.26, 250 times, and we get a negative 2,065 Newton meters. And then let's take our 27.57, multiply it by 450, and then I'm going to add it, and I get 14,000. That's actually negative 14,472. And we better hope that that 48.23 multiplied by 300 gets the same thing. Yeah, we're pretty darn close right there. There's some round off errors that are going on. So then we do the other side over here. We see that Raz is I called him the wrong thing down here. Oops, he was supposed to be Raz. I fixed it. He is 31.52. Okay. I'm just going to pick this arbitrary level right there. And that's technically going to be negative, right? So there's a negative 31.52. And then it's going to come down 53.06. So 31.52 and 53.06 minus, and we get 21.54. So that's going to be 21.54, and then we're going to come up 27.59. So 27.59, and we end up with like 6.50. It's actually going to be negative, and it's very small. So it's going to be negative 6 point, and it should be equal to this one here, actually, 48. Some round off errors. Okay, so we're going to come up to here, all right? And so that's going to be negative. And I'm actually kind of predicting that this is actually going to be come down here. So this is going to be like a zigzag one right in there. So let's see what that is. 31.52 times my 250. All right, so that's going to be negative 7,800 right here. And then we're going to go 21.54. and multiply it by 450, but it's going to be other direction. So sure enough, yes, it comes down over to here, but not by a lot. Right. So we get a 1,813, and it better go back to 0, but let's double check. So that's 6.048 times my 300. Yep, I get 1,814, right? So that's pretty close right in there. So, okay, so I've double checked everything and I believe them. Now we want to get the moment, right? The maximum moment. Okay, so it's either going to be here, or it's either going to be at that spot, or it's going to be at that spot. I'm pretty sure you can tell right there. So we'll say the maximum moment at A, or the moment at A, is going to be 2,065 squared plus 7,880 squared. I have it over here, so I don't have to actually calculate the thing out. And this didn't drop any, because we did it in Excel. It didn't drop anything. So I think I'm going to get 8,145 Newton meters. And then MB is going to be square root of 14,472. And that's so large compared to 1,813 that it's probably not even going to matter much. So it comes out to 14,472 582 Newton meters, so it didn't even change much. And so that's the max. So we're going to be designing the diameter locally for a single shaft. So a single diameter shaft, that's what I meant by that, at that one spot. What happened here? Little randoms. Okay, so what's our next thing? Oh, we need the material. All right, so I'm going to look up the material, and I lost my book. That's because, oh yeah. And that, remember, that was the ASI 4130 quenched and tempered at 540, and we're basing on yield strength, so we'll look at that for it. So let's take a look at yield strength. Okay, so looking through here, 4130 at 540, yield strength of 910. Did I do that? Yes, 910 megapascals. So from a table A20. Table A20. SY is equal to 900. Did I say 910? I think I said 910. 910 megapascals. All right, so to find for maximum shear stress theory, we can get a diameter, and I'm going to go ahead and just look up the equation that I previously gave you. Although I think I can actually remember it. Almost. Oh, almost. I'll look up that equation. Let's see. I wrote it down somewhere. I should have wrote it down somewhere. Should have an ME370 and in my notes, and I think it was class, oh, I forget now. Was it class 16? I think it was class 16. Yeah. And so, yeah, we could actually, let's look that up in the book too. I'll show you where you could find this also in the book. I have it here. So here's my, if it'll go to there. Here's the distortion energy theory. That's the equation for the diameter that I would use. Here's the one where I did it for maximum shear stress theory. You can see that I have my stress concentrations right in there as well. But let's take a look. Actually, I don't think this one is in the book. I think I can find something really, really similar, but it might be in an example somewhere. So I would give bonus points out, man. I should start awarding like bounty bonus points, right? So give me a bounty in the first person that's able to find the equation that will help me simplify the process or make it so other students can benefit from it. But yeah, so maximum shear stress theory isn't really, they use distortion energy theory mostly in the chapter 7 stuff. I'm referring to chapter 7 and the shaft designed for stress type of section. We will learn what the A and the M subscripts are. Those are alternating in mid-range. Yeah, but so anyway, this is the location that it might be in there, and they might even have like some static. They go through a whole process of designing this shaft in this one example. But I guess it's not in there. So we're just going to go ahead and write down this equation and use it. And we could have found it ourselves without too much difficulty. Let's just believe that's true. 32 design factor divided by pi yield strength and times the square root of KT M squared plus KTS torque squared the entire quantity taken to the cube root. So let's take that and take 32, and our design factor was 1.5, I think, and our yield strength is 910 E6 square root of our this guy right here. Let's see, this guy. Where'd you go? Or here. What do we use? We looked it up. 2.4. Is that right? Yeah, 2.4. 2.14. Times that moment we just found, 14,582 square them. And then take 3.00 and times the torque, which we found early on, 13,264. 13,200 264. The quantity squared, and that entire thing taken to the third. And let's see. Do I have that as I guess I can take the last little moments to do this. 2.14 times our 14,582 and square them, and then our 13,264 3 times, and then square them, add them together, square root them, multiply them by 32, multiply them by 1.5, divide by pi, get 910 E6, divide, and now we want to take it and raise it to the 1/3. Boom. And I get my diameter should be 0.09467 meters, aka 94.69 millimeters. And then I need to look that up in the table A17 and find my preferred size. So we do that, and in millimeters, 100. There you go. So that's the answer. Is D is equal to 100 millimeters. Preferred size. Table A17. And so here's my answer. Ta-da! And this was a very long video, but you could have fast forwarded to the end. One more thing for your own edification here. Okay, so I think maybe the original problem had it as 80 millimeters, maybe. I don't know. Actually, I don't remember what it was. But here it is as a spreadsheet. And here's like a previous year, but I went ahead and put in all these different values. And right here is the diameter, okay, of 80 millimeters, let's say. So this is 0.08 meters. And I come through all of this, and here's my stress concentrations, but I get 0.98 and 0.9. Let's say that and that's 0.9 in maximum shear stress theory. What I can use is my data and use the what if thing and goal seek, right? And I can set this cell to 1.5. Whoops. Let me go back forwards. Sorry. That cell, I need to close that, okay, to 1.5 by changing this cell up here. And I just hit go. And there you see it. I say that it's 94 points. I didn't like that. Yeah, 94. That's the right number. 94.69. There you go. Get the exact same thing. And I didn't have to do the algebra or do the thing backwards. So it's kind of a nice situation to have, you know, to be able to do that. And you can see I also have the distortion energy theory right in there as well. So this is a nice tool to be using. And that's the end of this video, a 44-minute video. Done.